So we're going to start with the disk, and the disk contains, as we said, 60 billion solar masses of stars orbiting in a particular direction. They are, of course, in Kepler orbits. Along with that is some gas and dust. We saw the evidence of this. Within the disk, there is a very exciting and interesting substructure, which is difficult to tease out, and it turns out that the stars in the disk orbit in many orbits, some of them more eccentric and some circular. But if you look for the concentrations of particular kinds of stars, blue stars, OB stars, the attendant ionized hydrogen, H2 regions that come indicate star formation, and to some extent the molecular hydrogen clouds, those are not scattered uniformly over the disk, but in fact are concentrated in these spiral arms, these linear structures that wind through the disk. Now, how are you going to find that if you're looking lengthwise through the disk? How are you going to recognize that there are discrete structures? Well, this is where the 21 centimeter hydrogen line gave us great benefit. So what happens is that imagine, if you will, that here we have our disk, and here is the center, and out here, about a third of the way out, is the sun. And imagine that the direction of the angular momentum is such that this is the direction of rotation. And what this graph shows you is the observations that you would get by observing 21 centimeter emissions from coming at the Earth from this direction. And what will happen is, I told you the 21 centimeter line is a very sharp line. And so, of course, because relative to the sun's motion in its Kepler orbit, objects at different parts of the disk are moving, there will be a Doppler shift associated to the relative motion of whatever is emitting the radiation relative to the sun. We can measure that Doppler shift, and what we find here is a spectrum of the observed 21 centimeter emission from a particular direction. And what we see is that this would be correspond to the wavelength 21 centimeters. We see that there is somewhat redshifted light coming in, and then a light with a slight blue shift, and then a whole lot of light received, or radio waves received, that have been blue shifted by various amounts. And typically, the way we draw this, or we are shown this when we are students, is a graph like this with three nice peaks in it, and we are given to understand, the way this works is that there are three clouds along this direction, each of them moving with the characteristic Keplerian velocity in its orbit, and these lead to three different Doppler shifts. And by noticing the three discrete Doppler shifts, we can realize that there were three clouds in the way, and by reconstructing, sort of doing a tomographic analysis as we sweep the direction in which we are looking, we can follow these clouds and reconstruct the structure of the disk. What's nice about this image is that it shows us more what real life is. These three peaks are in fact to be interpreted as a result of emissions by 20 discrete objects, because we know something about the line shape, and you can sort of do a fitting. This gives you a more realistic image of what astronomers are up against. With all that, they have come up with a pretty good picture of what the structure is in the Milky Way's disk, and here is an artist's conception of what this looks like. This is an artist's conception from circa 2008, and in the past decade, our understanding of this has changed. The Milky Way was traditionally thought to have had 4 large spiral arms. It turns out that now 2 of them, the Norma and Sagittarius arms, have been demoted to sort of secondary sub-arms, and the Milky Way really is thought to only have 2 large arms, the Scutum Centaurus arm and the Perseus arm. These emerge from the edges of the, as I said, newly discovered galactic bar. And you can ask where the sun is in this picture. That would be a good question. So the sun in this image sits about here, which interestingly is not on either the Scutum Centaurus arm or the Perseus arm. In fact, it lives on some sort of branch structure over here that is called the Orion Spur. And in addition, these recent discoveries include these two 3 kiloparsec arms that are very closely wound near the galactic bulge. So we've learned how to map the structure of the disk. It's important to remember, again, that what is concentrated along the disk are blue stars and ionized hydrogen clouds. There are stars and certainly gas elsewhere in the galaxy. How do we know this? Well, it's easiest to look at a galaxy we can view this way. So let me cheat history for a while and ignore the fact that we're in the 20s. This is a beautiful spiral galaxy M83. We can see the concentration of blue light indicating new hot stars and red regions indicating ionized hydrogen emissions in the spiral arms of the galaxy. But when we look at the same galaxy on the right, in the infrared, we see that the contrast between the arms and the rest of the disk is far reduced. There are stars, there is luminosity in the rest of the disk. It's just less of it is new blue stars and ionized hydrogen. Those are concentrated in the arms. It's very important to realize the space between the arms is far from being a vacuum. So we have the stars in the disk. Other than that, the disk, of course, is the location of most of the gas and dust in the inner galaxy. As we said, the gas is only 5 billion solar masses, so something like 7 or 8% of the mass of stars in the disk exists in the form of gas. This is mostly atomic hydrogen, some molecular hydrogen, some ionized hydrogen, and of course traces of everything else. The dust, as I said, is tracked well by the gas, as I said, is tracked well by dust, or the molecular hydrogen is tracked well by dust. In terms of mass, dust contributes very little to the mass of the galaxy. What is important about it, of course, is its optical properties. It does contribute to extinction. The dust and the gas tend to be confined to the galactic plane, in general more tightly than the stars, though we saw that there are excursions, and much of the dust and gas is confined to within what we call the solar circle, a circle of radius 8 kiloparsecs around the center of the galaxy, so about where the sun is. Past where the sun is, the dust and gas density drops off rather quickly. So that's the structure of the disk. What else is there?